Silence, Alex. Sorry, Alex, you're closest to the door, so you get all the work. So, okay, so we were talking about dielectric slab, and so we have something of refractive index N2 immersed in medium N1, and thickness D, and we considered a ray coming in at an angle theta 1, and a first surface and back surface reflection, and then we considered the field at these 2 points, because everything after that, moving through the lens, just gets us a common phase term, which goes away in interference. And what we found is that the interference over here was equal to what?
4 I1 sine squared of delta phi over 2.
Yep, 4 times I1 sine squared delta phi over 2, and delta phi is?
2 pi over lambda naught.
4 pi.
Oh, yeah.
Over lambda naught.
Times N2.
N2d cosine theta 2. Okay. So that was our result. We talked about Haydinger fringes. We talked about Fizeau fringes. What is the difference between Haydinger and Fizeau fringes?
Fizeau is a wedge.
Yes. So in both cases, we used the lens. For Haydinger fringes, what do we use the lens for?
The back focal plane.
Yes, to take parallel rays that focus at infinity and bring them into a focus at a finite different distance, namely at the back focal plane of the lens. For Fizeau fringes, what do we use the lens for?
Imaging.
Yes, to image a region of optical path difference. So that's the difference between Haydinger and Fizeau fringes. Yeah, Carlos?
So remind me, what makes these waves coherent, given that they're traveling a different optical length at the focal point?
So we said we had a plane wave. And specifically an electromagnetic plane wave. And a plane wave means what? It's monochromatic. If it's monochromatic, then what's the temporal coherence like?
Really good.
Yeah, perfect. Mm-hmm. Yeah, so any path difference won't matter as far as coherence is concerned. So just by virtue of the fact that it's monochromatic.
So in practice, since we typically don't have truly monochromatic sources, does the lens have to be a certain distance away? Like, can't do it too far away? Or?
Well, so from this point on, it's all a common path length.
Okay.
So it has no effect. The only difference in path length is right here.
So if that were incredibly thick, it would mess us up in real life. We don't have monochromatic sources. But there's no reason to make that work.
Yeah, incredibly thick in relation to the coherence length. So if you have a coherence length of, say, 2 meters, and a 1 millimeter thick piece of glass or quarter-inch thick piece of glass, it's going to be coherent. If you have a coherence length of, say, 10 microns, well, it won't be coherent. Okay. So, what we want to do today, and remember that this is an example of what kind of splitting to get 2 beams from one?
Division of amplitude.
Division of amplitude. So what we want to do now is look at a number of interferometers that operate by division of amplitude. And these interferometers are sort of the classics and are extremely useful and get used all over the place. So The first one is the Michelson interferometer. And first, I'm going to show you the really involved setup, and then we'll do the really simple setup. So, we'll start off with a monochromatic extended source. Monochromatic, we immediately know what?
Infinite coherence.
Yeah, high degree of temporal coherence, perfect temporal coherence, it's perfectly monochromatic. Extended source tells us what?
Point.
Coherence not perfect.
Yeah, we're going to have limited spatial coherence, depending upon how far away we are from it. Okay, so let's say that I have a beam splitter here, and generally speaking, you make a beam splitter by taking a piece of glass, and I'm going to draw this a little bit differently. And on one surface of it, partially metallizing it. So this is partially metallized over here.
What do you mean by partially?
Meaning really thin.
Okay.
Yeah, so it's a little bit transparent, but not fully transparent.
Okay.
Okay, so if we take, say, light from this point on the source, and we consider it traveling over to this beam splitter, we're going to ignore Fresnel reflection from the glass. We get refraction, and then some of this light gets reflected, and then it gets refracted up here, and let's put a mirror here, such that that light reflects, and then it's going to refract, and then we're going to look at the transmitted part of the light. So that comes down, out like this. So we've got basically these directions. And then let's consider, so that's the reflected path the light takes. Let's consider the transmitted path the light takes. And now notice the reflected light went through this piece of glass 3 times. So in general, we put another piece of glass in here. Let's do this. So that we refract through it, go out, and now I'm going to draw a little aid to my diagram here. And let's put a mirror right here. And then we reflect off that mirror, go back through the glass, and then come over here basically, and then reflect. So let me fix this a little bit.
That's just so they both went through the same amount of glass, right?
Yep, so each ray went through the glass substrate 3 times. Okay. All right.
What happened to the, we don't care about the reflected off of the second one?
Which one?
The second,
Here?
The second one.
This one?
Yeah, isn't there a reflected one from?
From the glass surface? Yeah, but we don't care. It's
Okay.
small. So we're not going to worry about it. Okay, so what do we have here on the output of this thing?
2 parallel rays.
2 parallel rays. How do we get them to interfere? A lens. So these guys, and we look in the back focal plane. And so that would suggest what kind of interference? Hager or Fazot?
Hager.
Yeah. And to understand why what we can do is take this transmitted beam that then comes back and reflects. This mirror plane is a plane of symmetry. We can take this path over here and unfold it about the axis of the mirror. And if we unfold it, then basically it looks like this. Where this surface, let's call this mirror 1 and mirror 2. This mirror 2 has a virtual image M2 prime back here. So it's like this ray got reflected off of a virtual mirror back here. We can think about it in that way. And then notice what we have here. We have two reflective planes that are parallel. Well, that's exactly the geometry of our dielectric slab. So everything we did for the dielectric slab pertains to this situation. So we could write down the interference here. The interference is just the same expression. The path difference, the phase difference is the same expression. What would D be here?
Distance.
It'd be this.
Between mirror 1 and mirror 2 prime.
Yep. Which is the same thing as saying that if this path is D1 and this path is D2,
Just D1 minus D2.
yeah. Okay, so you see how that maps onto this situation? Okay, so if I look in this plane, what will I see? This plane, what do I see?
The same thing as before.
Same things we saw over here. What do we see over here?
Fringes?
What do we see?
Concentric circles.
Concentric circles. That's right. In fact, let me draw them. Let me draw them over here. These concentric circles. I'm just going to go crazy and draw a lot of them. Okay, so basically this plane, we're looking pretty much right there. Okay, what would happen if I took mirror M1 or mirror M2 and started to tilt it slightly? Just this orientation. If I tilted it slightly.
You're going to start separating those beams.
Yeah. Yeah, there'll be a little more angular deviation.
Those circles become more oblong.
Not quite.
The electrical path length change? Because the angle off the mirror.
The optical path length,
The
a little bit. So if we tilt this a little bit,
Or will we get more of like a Friseau fringe because they're now going to be diverging, and then we're going to be passing through a light and bring it back together to focus.
right? And if we have just a tiny amount of tilt, then we're not going to be very far off the imaging condition here. But you're absolutely right. As we tilt it, then we're going to get into a Friseau fringe situation where we want to look in the image plane of the lens. But as we just barely start to tilt it, then the image plane isn't very different from the back focal plane. And so what happens is that circular fringe pattern gets moved, just shifts. Which you could also visualize as circular fringe pattern, and now you just shift it over where you're observing the fringe pattern. And as you continue to tilt this, then basically you're moving this more and more over, and now your fringes over here, they start to look like just lines. Because you're so far away, yes. Exactly. So you've just transitioned from basically Haydinger fringes to Bazofres. That make sense? That make sense? Okay. So forgetting all the math, just going back to here, parallel planes, circular fringes centered on the axis of the lens, tilted just infinitesimally.
Only M1?
Yes, only M1. Just tilted infinitesimally, and basically that circular fringe pattern just moves over a little bit.
Why is that? Like, what? With the lens there, I imagine the angle of the rays must change coming in. Is that what's happening?
Mhm.
Therefore, it's changing the focal or the.
Yeah, the centroid of the
Yeah.
pattern, yeah. Pretty much. And so as you keep moving it, you're just taking that concentric circular fringe pattern and moving it off center.
If I tilt the mirror in the other way, will the fringe shift in the other direction?
Shift in the other direction. Or if I tilt in this orientation instead of this orientation, then I'd be moving up and moving down.
So do the concentric rings stay put at where we're looking at is shifting?
No, it's actually the ring pattern is moving where we're looking at, stays fixed in space. But we could mentally adjust our attitude to looking at it this way.
But only one.
Yes. Only one moves.
I don't see how the angular change through that makes it through M2. So like, if M1 does induce a slight angular change, after it hits M1, it's not going through M2 again, according to how we drew it.
Oh,
So
well,
how do those end up parallel at the
well,
end then?
so the ray that goes and hits M1 never hits M2.
Yeah, so if there's an angular change on the ray on M1, how does it end up still parallel to the one coming off?
It isn't
M2?
parallel. It's a little bit of an angle.
Okay, so.
But the
now-
net effect for small angular deviations is to take this and shift it.
As though it were a parallel being changed.
Mhm.
Okay, that's what I was.
Yes. That's right. Okay, so this is the involved geometry. Now let's look at the simple geometry.
Can I ask you a quick question? Huh?
Sure.
Does D1 have to be bigger than D2, or could it
No.
be? Okay.
Could be the other way, but that's fine. Okay, now, let's say that we have a collimated monochromatic source. Or at least quasi-monochromatic. And so collimated means what?
Parallel ray?
Yeah, so it's basically a truncated plane wave. So plane wave technically extends through all space and time. If you just take an aperture and pass the plane wave through that, then, and forget about diffraction, then it's basically that restricted lateral direction plane wave moving in whatever direction is possible.
It's a plane wave of a
Limited spatial
size.
extent. So it's an idealization. But basically it's take a laser beam, expand it, collimate it, so it's all kind of going parallel, and it'll stay that way for a while. That's basically the situation. So let's say we have a collimated monochromatic source, and we come into a beam splitter, and I'm just going to draw one ray because all the rays are the same. They're just parallel to the one ray I'm drawing. And then some of it reflects, go up to a mere M1, so it goes up, comes back. Some of it transmits, go to a mere M2, reflects back. And then if M1 and M2 are perfectly aligned, then those rays basically fall on top of each other in the output port. Okay? And now let's say that we put here an observation screen. Then first question is, what will we see on this observation screen?
See the result of being either constructive or destructive interference due to the path length, right?
Uh-huh.
But there's no lens.
We just
But
look
they're
at-
right on top of each other.
Right on top of each other.
They're superimposed.
Hmm?
They're kind of superimposed.
Still didn't get it.
They're kind of superimposed, right?
The rays are
The rays.
superimposed.
Superimposed,
and it's coming
yes.
out.
Mhm.
Yeah.
Yes. So basically, you have a beam coming in, some of it reflects, comes through, some of it transmits, then reflects. So those two beams are sitting right on top of each other.
This is a special case of Nicholson. No.
Yeah,
Yeah.
in some sense, yeah. So what do we see on this observation screen? That's the question.
You see a dot. You just see a dot.
No? And you don't see the same thing as this? So for the beam that takes the upper path and comes down, what would we see if we only saw that beam? Collimated line. What does that look like on an observation screen?
Big
Dot?
Spanish, like lots of power in the middle.
Like a
Well,
Gaussian
let's idealize it that it just has sharp edges and it's a flat top.
Square.
So won't we just see the beam?
Yeah. Yeah.
And it'll be uniform intensity?
Big dot.
Well, yeah, I wouldn't call it a dot,
Okay, that's
but we just see
okay.
a
A
beam.
beam. Got it.
Yeah, and it will have some uniform irradiance across the entire beam width. Okay, so that's for the upper one. What about for the lower one? What would I see?
Same thing.
Same thing. Okay.
But is kind of, if you move a mirror, getting those amplitudes to add up, you could dim it or brighten it, right?
Yes, that's
Yeah.
exactly the point.
Yep.
Because the irradiance here is going to be, we've got collinear beams, so I1, I2, 2 times square root, I1, I2, cosine of the phase difference, right? It's always how it is when we have collinearly propagating beams. And spatially, every place on here, it's the same thing. So that means we're just going to see something uniform there. What will we see? Well, it depends on what delta phi is.
Which depends on the optical pattern.
Mhm. And so delta phi, what's it going to be? Just thinking about it a priori, let's say that this is length d1, this is a length d2.
So K, G2 minus D1, or
So, and k is
2 pi over lambda.
2 pi over lambda naught times refractive index of whatever this is immersed in,
D1 minus D2.
times d1 minus d2, let's call it delta d.
Yeah.
But there's one little subtlety. This light travels d1 twice, this one travels d1 twice.
D2 twice, right? So
Yeah,
it's
so
2
it's
D2.
2 delta d.
So it ends up being the same thing. It's kind of
Yes,
more.
where theta 2 is 0.
Yeah.
Yes, exactly. Exactly right. Okay, and then as long as this is a 50-50 splitter, then I1 is going to be equal to I2. And so we have basically 4I1 cosine squared delta phi over 2. Now, why is it cosine squared instead of sine squared?
We didn't apply some sort of trig identity.
No, we did. I mean, we did a half angle formula in both cases. To get, I mean, here, we ended up with 2i1 plus 2i1 times cosine delta phi. So that's 1 plus cosine delta phi, which is cosine squared of 1/2 delta phi.
You're asking like, why does that make sense, right?
No, it's just, why do we have cosine here and sine there?
Because there was a plus note instead of minus in the derivation.
Remember here, we had R21,
Yeah, it
which
was
is minus R12. So we have a minus sign. So we have an extra pi phase shift at that interface, which is a pi in delta phi. And so that flipped the sign, and we ended up getting sine squared instead of cosine squared when we do the half angle formula.
Could you one more time go over how D1 and D2 gives us to D?
So the light that goes in the upper path travels D1, and then D1 again, so that's 2D1.
Correct.
And this goes D2, and then D2 again, so that's 2D2. So the path difference is 2D1 minus 2D2, which is 2 times delta D, which is 2 times D1 minus D2.
Oh,
Yeah, it's just because we're traveling that path twice, up and back. Okay, so are you okay with the cosine squared instead of the sine squared? Okay, it's just because here we don't have that extra pi phase shift upon reflection. Okay. So basically then, for some delta D, delta phi just has some value, so the cosine squared has some value. So this I will be some value everywhere. So we'll just see uniform irradiance. If you will, a uniform fringe. So what does the irradiance do as a function of delta D?
Gonna go down to 0 and then back up. and
Mhm.
back down.
Yeah, we'll basically be doing this. So the light here could be bright, could be gone, or could be anywhere in between. Okay, so if it's, well, actually, let's do this one first. If it's bright, then this corresponds to 4 times I1. How can we possibly get 4 times I1?
The time average is still 1, right?
No.
Are you asking like physically, like how does that happen, or like why is that possible, or?
I'm asking, do we have an energy conservation violation?
At first glance, yes,
I mean,
but it can't.
Yeah, at first glance, it's looking pretty funny, but we know that can't happen. So that means there's something wrong with our initial thinking. And it goes back to, what is I1 in the first place? So if I write this down, what's I1?
That's the intensity of the starting beam, right?
No, it's half of it, right?
Well, it's the irradiance of the beam that follows the number 1 path,
And comes to
the irradiance here.
Yeah.
Likewise, I2 is the irradiance of the light that follows the number 2 path here. So we need to figure out if this is irradiance, say I0, coming in, what's I1 in terms of I0? And if this is a 50-50 beam splitter, then in this direction we have I0 over 2, and this direction we have I0 over 2. And then coming back, this I0 over 2 half of it goes in this direction, half of it goes in that direction, right? And likewise for this one, half of it goes in this direction, so I naught over 4, half of it goes in that direction, I naught over 4. So apparently, I1, which is I2, is I naught over 4. Therefore, this is just I naught.
But now, if you have I naught coming out, but you also reflected stuff, then what?
Yeah, exactly. So if delta D is set so that I'm here on this port, it means all of the power is coming out here. And so none of the power is coming out this way. So these two must be destructively interfering.
That is so weird.
Destructively interfering with each other.
Yeah.
Yeah.
Yeah, so in other words, when the phase shift here is, and well, if we shift this over so that when that was 0, then the phase shift here is going to be pi. So they destructively interfere.
So the energy is all just in the output and not in
Yes.
the reflections. Well, not just those reflections, but any other reflections off that beam splitter too, right? That aren't going down.
Yeah. Well, it turns out that accounts for all of it.
So then if we flip the output off, would we be blasting all of our light back into our laser?
Bingo.
I'm about to say
Exactly. That's exactly what we'd be doing.
That sounds bad.
Yeah, generally that's not good. But in essence, this Michelson interferometer is a 2-port device. It has 2 output ports. One of the output ports is this way, one of the output ports is that way. And so this output port is also the input port. So when we adjust these paths and we're moving here, then basically we're adjusting the power splitting between the 2 output ports. And we could adjust it so we have equal amount of power out of both ports, or all the power here, or all the power there, or anything in between. Okay, so that is really important to understand. Now, okay, yeah, we'll see that in play with some other parameters too. All right, so are there any questions? All right, so if, now let's play the same game.
Actually, I guess I have one question.
Yeah.
How close to the same distance that D1 and D2 have to be to actually meet that exactly for I1? Like, what's the kind of, like, I'm sure it'll be in terms of lambda, right?
Yeah.
So how close?
So it has to be a small fraction of lambda.
Okay.
Yeah,
So
so
just-
if you're, say, green light 500 nanometers, then your path differences ought to be, say, 20 nanometers or less.
Okay.
And you think 20 nanometers, oh my gosh, that's small. 0.02 microns?
Yeah, how do you manufacture mirrors so exact?
That's actually not too bad. It's more the positioning accuracy.
Yeah.
That's what
Some
I'm
really
saying.
good micrometers.
Yeah, really good micrometers. Yeah. Okay. So we need to explore 2 other variations on this. First variation is, what happens if I take mirror M1 and I start to tilt it a little bit? Well,
Yeah, they're not going to interfere.
yeah, well, the light that travels this path is going to be at a bit of an angle here, right? Yeah, now you haven't done, I assume, homework number 5 problems, whatever, the last couple of problems. But when you do the last couple of problems, what you're going to find is that whenever you have plane waves propagating an angle, and you look in a plane nominally perpendicular to them, you'll end up getting spatially varying fringes. So when you work that problem, just pay attention to that. And so here, basically, if I tilt that, I'm going to have light coming in at two different angles. I suppose one of them's gonna be parallel, one's gonna be off if I only tilt that guy, but whatever. And so that's going to give rise to a spatially varying fringe pattern. So what happens when I tilt this guy? Well, I go from a uniform irradiance to spatially varying fringes. And the more I tilt it, the closer together those fringes are. So if we had a lab in this class, that's one of the things I would do is have you build this setup, looking in that plane, and try to get these things perfectly aligned so that that is uniform. And when you do this, of course, you're not perfectly aligned. You have fringes like this. And so you know you're getting close on the alignment when these fringes start to spread apart. And then the angular orientation of the alignment tells you which axes of the mirrors you need to be adjusting.
So does it just spread out until you have uniform intensity? Or? Okay.
That's exactly right. At which point these two are collinear. Okay, fine. Now let's look at scenario number 2. Instead of monochromatic, let's say we have limited, well, we have some nominal spectral width. So if I look at delta D, when delta D is 0, what's going to happen with the irradiance here? Even, no, go ahead.
It's going to be 4 pi or 4 I1 here.
Yeah. It'll be at 4I1, or I0, I guess we called it.
What other condition did you say we set up here?
Let's say it's no longer strictly monochromatic, let's say it's quasi-monochromatic.
Oh,
So now let's say I start to change delta D. What
Wait,
will I
it would
see?
be 4I0, right? It'd be either 4I1 or
Oh,
just
sorry.
I0.
You're right, the I0. Yes, perfect. Okay, so I change mirror position. What happens?
Like just the distance?
Yeah.
So it's going to drop off again. Right?
Yeah, so it'll do this, right?
Do the cosine thing.
Yeah. Okay, what if I change the mirror distance a lot?
I feel like then it's going to stop interfering, right? If you get too far.
Yeah, under what condition?
The coherence length.
If 2 delta D is much bigger than the coherence length, then they won't interfere anymore. So at some point I'll be far enough away that I'll just be 2I1, which is I naught over 2. And likewise, if I go the other direction, eventually I'll get to the same thing. So the question is, what happens in between these things?
same thing with that slit, or the slit experiment, where you get an
Yeah,
envelope.
it's just going to
envelope.
kind of fizzle out.
Yep. And what will this envelope be?
The coherence length? Or
The,
Temporal coherence.
it'll be the coherence, gamma 1, 1 of tau.
okay.
Where tau now is mapping onto the delta D axis. So in other words, I can measure the coherence of the source with my interferometer, measure the temporal coherence of the source. Now, does this make sense to everyone, this picture? Yeah,
Yeah, could you re-explain that again? I was a little lost as to how it fizzled out.
So,
Depending on the.
so if we have a quasi-monochromatic source, it'll have some coherence length, L sub C. If D1 and D2 are the same, then, I mean, we're so much smaller than LC, we'll get interference.
Oh, gotcha. Mhm.
So in here, we're getting interference
Gotcha.
because delta D is small compared to this. In fact, maybe we ought to put that condition right here. 2 delta D is much less than LC. And then as we move this guy way out, then we're over here where 2 delta D is much bigger than LC. Or we go move it way in, 2 delta D is much bigger than LC. And then in between, well, we're going to transition from being much smaller than LC to on the order of it, to bigger than it, to much bigger than it. So we'll see our fringes wash out as we have more reduced interference because of the reduced coherence. Okay. So is that making sense?
So if that's the coherence time, right? That length one.
Mm-hmm.
How much is it like wobbling by then? Is it like not at all, or is it like most of the way there to flat?
For what condition?
I guess it'd be fully. I'm just trying to think. So we kind of drew this dashed line.
Mm-hmm.
That's the coherence time, right?
That's
Or
the actual coherence, where the tau maps onto delta D.
Okay.
Because delta D is just difference in propagation time between
Yeah,
those two
yeah.
paths, which is
Okay.
tau.
Okay. I was just thinking, like, is the end of that dash line like where we're flat again, or is that just where it's like wobbling, like kind of so low
Here?
that we don't care? Yeah.
Yeah, then it gets back
Or is it just
to
arbitrary?
what are we trying to do?
Yeah.
But yeah,
Okay.
it'll wash out,
Okay.
and ultimately it will go completely flat.
Okay.
Okay.
So out in those flat regions, we have I naught over 2 is the radians.
Yes.
We have 2 of those, I guess, we said.
Well, 2 I1s, and an I1 is I naught over 4.
Right, but we'll have 2 beams that each have that intensity? Or?
Oh, yes, one beam going this way, one beam going that way.
Yeah.
Oh,
Because they're not interfering, so
Yeah.
it's just the beam splitter splitting in half.
Got it.
Yep. That's it. Yep, so power still conserved? Okay. So, any other questions on this one?
Okay, so conceptually, it makes sense like how all the energy is conserved, but like how does energy in one place know not to be there,
Oh.
and energy in another place know to be there?
So this gets into all the quantum conundrums.
Okay.
Yeah. It's like when you set up the Young's double slit, and you have a source here, but this source is so low in power that you basically are emitting individual photons, every so often. And then the question is, where will they end up over here? I mean, how can one photon see both slits? And it turns out that if you measure where the experiment's been done, if you measure where the photon ends up, it'll be somewhere on there. And then you do the next photon, it ends up somewhere else. The next photon ends up somewhere else, whatever. And you keep doing that and build it up over time, then you end up with the fringe pattern for a bright source. So basically, this thing imposes a probability distribution function on where the photons land. And so how do you interpret that? Well, you can interpret it as saying, well, the photon, even though it has to go through just one of these, somehow sees the other one and that affects where it goes. Well, whatever. However you want to think about it, I don't care.
Because if you cover one of those up, you get a different pattern, right?
Oh yeah, then it just becomes uniform. Yeah,
That is weird.
it is weird.
I thought a single photon still made a wave pattern. Was it the accumulation of all of them then?
Well, a single photon you can,
I mean, the energy's so low, but.
yeah, I mean, so in the photon model of optics, because remember, we have to go back to what model we're talking about. And the photon model of optics, you cannot take light of a particular wavelength and reduce its power anymore. than what you have in one photon. Yeah, so that becomes fun.
As in, they're still trying to figure it all out.
Yeah, no one has a good explanation that I've ever heard. So, okay, so we've got a picture then of how this works. Now let's talk about some applications.
One other quick question.
Mm-hmm.
Given the setup you just erased,
Mm-hmm.
is there some, let's say, if we had it to where it would be full reflection back into the laser, is there actually any delay time between when the laser's turned on and that actually happens?
Yeah, it's just the propagation time.
Is the propagation?
Yeah, that's it. So in other words, there'll be a transient setup time for it to reach steady state. So then you could ask, well, what if I turn on and off my laser at a time faster than the transient setup time? Well, it'll never reach steady state. All you'll have is a series of transients. But it'd be straightforward to figure that out. Okay, so for an application, we're going to get at it in a roundabout way. So let's say that we have some sample, and we want to measure its absorption as a function of wavelength. What do we do? Well, generally, we just go to a spectrophotometer and measure the absorption as a function of wavelength. So how does that work? Well, with a spectrophotometer, what you begin with is a broadband source. So if we look as a function of frequency at the power spectrum, you know, it does something. It has some broadband emission spectrum. Okay, then we collect that light and run it through a monochrometer. And the purpose of a monochrometer is basically to have a very narrow bandpass. I mean, it is a very narrow bandpass filter. So if we look at the, let's say we look here at the transmission as a function of frequency, it's basically just a narrow bandpass filter. So if we take this and put it through that, then at whatever frequency we're sitting at, you know, we're just going to carve out that part of the spectrum and pass it through. Okay, so now we have a narrow band beam. And we take that and pass it through our sample. And then we run that into a detector and measure how much power we're getting through the sample. And now to get the full spectrum, absorption spectrum of the sample, what we have to be able to do is this monochrometer, we need to take that narrow bandpass filter and scan it in wavelengths. So, you know, we start, say, over here, make a measurement for wavelength mu1, shift it over a little bit, make a measurement for mu2, shift it over a bit, mu3, etc. And what we'll get is the power spectrum coming through the sample, which will basically be that power spectrum with whatever absorption of the sample impressed on it. So it'll do, I don't know, let's say that. So I've knocked out a bunch of this stuff. Does that make sense? Is that okay, Carlos?
Yeah.
Okay. So what we want to know is what is the transmission as a function of, let's say, frequency, wavelength, of our sample? Well, it's just going to be the power spectrum of the whole system with the sample in it divided by the power spectrum of the source. So in other words,
Source after going through the monochromator?
before the monochromator.
Before, okay.
Yeah. So the monochromator, all it does is it allows us to make this measurement wavelength by wavelength.
Mm.
So we scan in wavelength, so we get this in wavelength.
When we scan in wavelength, we're changing the monochromator.
The monochromator. Mhm. Exactly.
And TV, what's that again? That's just the
That's
transmission?
that's the transmission of the sample. And the transmission of the sample is basically e to the minus absorption coefficient is a function of wavelength times the thickness of the sample. And basically what we're doing is we're trying to measure that absorption coefficient as a function of wavelength or frequency. Okay, so that's generally how you do it. And just as an aside, how do you build a monochromator? You take a broad spectrum and carve out a narrow piece. Bragg grain? Fiber Bragg grain?
Well, Bragg-Rainier.
Bragg-Rainier, okay.
Whole bunch of different,
Whole bunch of different.
receivers, I guess, for each wavelength, so to speak.
Yeah. So let's do the simplest possible one. Let's take a prism, polychromatic light. What does the prism do?
Split it all.
Splits it up. And what gets deviated the least and what gets deviated the most? Let's say it's visible light. Does it go red, green, blue, or does it go blue, green, red? How do we tell? What we have to know is what's the dispersion of the glass. And we'll talk about dispersion at the last couple of lectures of class this semester. But basically, dispersion says refractive index is a function of wavelength. And normal dispersion always goes like this. So shorter wavelengths, higher refractive index. That's normal dispersion. We'll talk about anomalous dispersion. So if this is true, if the glass has normal dispersion, is it red, green, blue, or blue, green, red? Why?
Because the blue will see the highest index, so it'll get bent the most. It'll be bent down to the bottom.
That's right. So blue has the greatest angular deviation.
I was thinking as I was looking into my kids, they had some weird glasses that made rainbows and everything. But red had the larger distances on those.
Well, you'll see why in just a minute. We'll talk about that. Okay, so then here, all you have to do is take a narrow slit and move that slit, and now you're just picking off a small part of the spectrum. So that's the conceptually easy way of making a monochromator. So that's,
As far as microwave precision.
yeah, but that's not so hard. It's not too bad. Okay, so that's one way to do it. That's with a prism. There's another way to do it, and that's with a grating. So if we have a diffraction grating, and we look in the +1 order, so we have the 0 order that just goes through, and the +1 order, it turns out that the different colors
It'll be just like a prism.
get deviated by a different amount. But the question is, does it go red, green, blue, or blue, green, red?
There's diffraction in my kids' glasses.
Yeah.
Yeah, the red diffracts much further.
So this angle, theta, goes as wavelength divided by the period of the grating. So the period of the grating is fixed. So that means red light is going to deviate more in angle because it has a bigger wavelength. So it's exactly the opposite. Okay, and so here then again, you can just take an opaque screen with a little slit, scan it, and now you've got a monochrome. Okay, so now we know how this monochrometer is made. Although, you'd really like to have a monochrometer where you have a beam come in, and then collinearly, that same beam coming out, with no angular deviation, no spatial deviation. You just want it to go collinear all the way through. So that's where the complicating factors happen. Because, here you've got angular deviation as you move the slit, you've got spatial deviation as well, likewise over here. So it becomes a matter of, well, how do you construct something to get this kind of geometry, because that's what's most convenient in an instrument.
Is rotating the prism or the grating out of the question?
No, that's legal. You can do it. Yeah.
Wait, so why would we care if it went straight through?
It's just, instrument-wise, it's just more convenient. So, if you change this wavelength, and this was now coming out at a different angle, then all this stuff needs to come out at that different angle, or you're going to be sampling through a different region of your sample, and just introducing all kinds of errors. So, but that's a topic for another day. Okay, so what the heck does this have to do with Michelson interferometers? Nothing. So if you have a sample and you're trying to make this measurement, say from the UV to the near IR, this is the way you want to do it. Works great. So a typical spectrometer will often have a range of 190 nanometers on the short wavelength side to maybe 1900 nanometers on the long wavelength side. That's pretty typical for a spectrometer. What if, on the other hand, you needed to make a measurement where your wavelength goes between, say, 2 microns and maybe around 12 microns. So now you're in the mid and far infrared. The question is, can you do this? Turns out the answer is no, for 2 reasons. One, you don't have any good sources that are bright and broadband in that range. I mean, you could argue with that and say, what do you mean? Just a heater, that's a good broadband IR source. And that's true. But it turns out it's still problematic. And then the other thing is that every single element in here is a source in that wavelength range because of black body radiation.
Yeah.
So how do you measure the absorption of a sample in a system where everything is glowing in the wavelength range you care about? I mean, that's a big problem. So that's where the Michelson interferometer comes in. So basically, what one can do is, let's say that this is your setup, and you have some broadband source over here, namely a heater. Then you're not going to be, I mean, you don't have a monochrometer in the setup, so you're not going to be doing anything with spectral filtering. But the thing you can do in a Michelson interferometer is you can take a mirror and wiggle it like this. Right? That's easy to do. And then your detector down here, what's it going to see?
It's going to see the middle of that.
It's going to see this thing right here. So you're measuring that by just looking at the envelope of the fringe pattern. So that means that you just measured the coherence of your source. And then take this and Fourier transform it, and what do you get? power spectrum.
And that's for done at IR because everything's glowing.
Yes. So now you know this, and you're trying to get that. So the next thing you do is, in one of these arms, stick your sample. And then do it again. And your fringe pattern is going to change, the envelope is going to change because of the absorption of the sample, which changes the spectrum, therefore it's changing the coherence. So you measure that coherence for the sample, then Fourier transform again, and now you have the sample source spectrum, or rather the sample spectrum. And then it's just back to this, and you're at the same point. And you've got the transmission for the sample, therefore you've got the absorption as a function of wavelength. And this is called a Fourier transform infrared spectrometer, an FTIR.
To get like cool the mirrors or something to keep them from heating up too.
No, no, you're okay.
They're just reflective enough that.
Yep.
Yeah. Now to actually measure this, are you changing your light source across frequency and just taking multiple measurements?
No, your light source just stays the same.
Just say this, so it's still broadband.
Yeah.
Still broadband.
Yeah, but you're still suffering from the fact that it's relatively weak. So if you do one scan of this, meaning one cycle of mirror movement, you're going to have a super noisy measurement. So the beauty is you put this on a piezo stage, and you run it at, I don't know, say a kilohertz. So you're getting 1,000 of these per second. Maybe run it for 30 seconds. You got 30,000 of these, average them together. You just beat your noise way, way down and have a beautiful measurement. So that gets around the low source emission problem.
So could you use this as a lower spectrum, the higher, the UV and near ion?
Yeah, you could.
Same setup would work. It's just
Absolutely.
less
More-
convenient.
Yeah, it's just more work. Yeah, this is easier. So, now it turns out that chemists use FTIR spectrometers all the time.
My wife does this.
Really?
Yeah, she's a chemical engineer. She does this.
Okay, so now you know how it works. Yeah. So the reason why chemists do this is because chemical bonds have resonances in this wavelength range. So for example, if you look at the carbon-oxygen double bond, it has a stretch resonance at 1,700 inverse centimeters, which is a weird unit, and it's actually 5.9 microns. That's a unit we like better. But the chemists, for whatever reason, they measure wavelength as 1/over the wavelength in centimeters.
So it's frequency-ish.
Yeah, frequency-ish. So if you're at, say, 1 micron, that's 10 to the minus 4 centimeters. So that means 1 micron is 1/10 to the minus 4 inverse centimeters, which is 10,000 inverse centimeters. If you're at 10 microns, that's 10 to the minus 3 inverse centimeters, so that's 1,000 inverse centimeters. So for whatever reason, the chemists like to show the wavelength in those units. But it's easy to do the conversion. It's not a big deal. Okay, so any questions? All right. So, an actual, honest to goodness, application of needing to measure coherence.
They use the same interferometer when they were measuring gravitational waves too.
Oh, yeah,
Yeah,
yes,
they just measured the space dilation down the two paths.
yes,
Yeah.
that's exactly right. Yep.
How did you say, or you move M2 again? What was the purpose of that? That was to just get the varying envelope? Or?
Yeah, you're basically scanning here in delta D
Yeah, if it's fixed, you get 1 point. on
with a
the
single
waveform.
detector. So you're scanning this whole measurement. You're making this measurement in time as you move this in time. And as long as you have a piezo translator, you can do it fast. Yeah, so this is how you measure gravitational waves. Well, this same instrument, although,
Much bigger.
yeah, have a few kilometers for path lengths here,
Yeah.
and then have this unbelievably low noise electrical detection system. It's pretty crazy.
And they actually measured it in 2 different ones at the same time.
Yes, yeah, which is way cool.
Yeah. I read an article on it, and apparently the third one was down for maintenance, and if it had been up, they would have been able to triangulate exactly where they came from.
Yeah.
But right now, they just kind of have a cone.
Right.
It came from this area, but
Right.
I don't know what created it.
Yeah, which is really cool. Okay, so maybe to finish out our discussion, how many of you guys have something like an ocean optics spectrometer in the lab? Yeah, we do. So the way that works is actually different. This is the old school way to measure a spectrum. The newer, easier way to do it is have some source, and let's say the source you put into a fiber, and so you just got this fiber, and then you've got light coming out of it, collimate it, and then capture that with another lens, focus that down into a fiber, and then run this fiber into your spectrometer, and then this comes out, kind of collimate it, and then run it into a grating like this. And then over here have a linear detector array.
Mm-hmm.
And this basically, each wavelength focuses down to a different pixel on that linear detector array. So then you can just measure the entire spectrum in one shot. And what you do is measure the source spectrum, so now you've got this, then stick your sample in here, measure the spectrum, now you've got that, so take the ratio, back out the absorption coefficient as a function of wavelength, and you're done. So, works really nicely. And this is cheap compared to that. I mean, you can buy a system like this for just a few $1,000s. Although the one we bought was about $15,000. And the reason why is because we wanted really low noise, so we paid for it. And low noise means this silicon detector array, linear array, you put it on a TE cooler, a thermoelectric cooler, that uses the Peltier effect to reduce the temperature of the silicon, and then that reduces your noise. So that works pretty good.
What did you call this one again?
It's a spectrometer.
So ballpark, how much did the upper scenario cost?
So way back when, I want to say 15K, 20K, 25K. But I haven't priced those in probably 15 years. So, when I was a grad student, that's all it was. It was this big hulking thing that was kind of a pain. And now this, it's just a little tiny box.
And you just have a little fiber.
Yeah, it's so convenient. Yeah. Okay, any questions? All right. So that takes us to the Twyman Green interferometer. I think what we'll do is save that for next time and call it a day. And so next time we'll do the Twyman Green, Magnac interferometer, laser gyroscopes, all that stuff. Okay,